Today we want to take a look at the problem that we had yesterday, which is to find the slope of the line tangent to the function f of x equals square root of x at the point 4, 2. 4, 2 is a point on the graph of this function. And this is going to be a parabola. And our goal is to find the slope of the line tangent to this curve at this given point. To review the problems that came up yesterday, not the problem that we were working on, the problem with trying to make this calculation is that slope wants 2 points. The slope formula is change in y divided by change in x, or y2 minus y1 over x2 minus x1. So the problem is the slope wants 2 points, but we've only got 1 point. Slope formula wants 2 points, but we've only got 1 point. Slope formula wants 2 points, but we only have 1 point. We've only got the 1 point for 2. If I try to put 4, 2 in for x1, y1 and x2, y2, I get 0 over 0, which is indeterminate. That's not helpful. So our strategy was to pick a point nearby. And the way I phrased this was pick a point nearby, and I told you how far to go. So I gave you a value of h, which is a little bit farther away from the 4. So yesterday, when I said we're going to calculate the slope, so we're going to choose a point. Our strategy is to choose a second point on f of x equals square root of x that is nearby, a little further away, a little close to 4, 2. We're going to choose a second point on the function that is close to 4, 2. And then yesterday on the handout, I defined different close to's. So the way I did this was the close to so h is equal to 0.5. That is, look at what's going on at 4.5. Remember that our strategy is to use the slope of the secant line to approximate the slope of the tangent line. And we get a better approximation if we move these points closer together. So we improve the approximation using smaller values of h. So I set 0.5 as a start, and then we made this h smaller. So our x1, y1 will be the point 4, 2 that we start with. So I'm going to make x1, y1 That's going to be the 0.42. And for x2, y2, I'm going to take 4 and add a little bit. And the y coordinate will be the square root of whatever that number is. So I'm going to find the slope of the line between these 2 points for different values of h. This is what it would look like with h. We didn't have to write this, but this is what it's going to look like. This is the plan. Note that the denominator has a 4 plus h minus a 4, so we're just going to divide by h. So for various values of h, we'll get different values for the slope. So I'm going to take my numerator to be the square roots of 4 plus 0.5 minus the square root of 4, which is 2. I can simplify that one. Let's just do this. That's my numerator. And then I'll divide by the denominator, which is just going to be the 0.5. That 4.5 is the 4 plus a little bit extra. This is a point that's close to 4. And we get this, 0.24264. I think I asked for 5 significant figures because I like to have excessive amounts of significant figures. So the slope of the tangent line is approximately 0.24264. Then the idea is to just use a smaller value of h. So when h is equal to 0.1, we'll get a different value of the slope. So then I'll just redo this calculation, but change my 0.5 to a 0.1. Goes up in 2 places. And now I've got a slope of 0.24846. So when we move h closer, we got a slightly steeper slope. We got a larger value for h. We go back to check to see if that tracks. And if we look at the way that this function is bent, this function is bent down. So it makes sense that if we pick a point further along, it's going to be a little bit flatter than the slope that we're after. And then if we move that point closer in, that's going to give us a steeper slope as we approach the tangent line. Then we just do this for even closer values of h. And this was the idea of the problem yesterday. 24984. Any questions? This was the exercise that we had yesterday. We highlighted the problem that we had. We want to calculate a slope. It requires 2 points. Tangent line only has 1 point that we know about. So we approximate with our tangent line with the secant line. And then we just move the 2 points from the secant line close together and see where things are headed. We have a pretty good advantage that some of you knew that we're headed towards a quarter because you have secret math knowledge. You know what the derivative of this function is, and you're able to plug in 4 and get 1/4. So you know we're headed towards 1/4. A great question came up yesterday. So we're trying to figure out what the slope of the tangent line is. And so I keep moving this point closer, and our approximation keeps getting better. So the question came up, how close do we need it to be? And unfortunately, the answer is eventually you'll just know. That just takes time. When you're driving your car and you need to make a right turn, how much do you turn the wheel? How many degrees does it go through? That's not how we know, right? Eventually, you just know. You need to stop your car. How hard do you hit the brake pedal? How many newtons of force is required to stop your car? Don't know, but you do know. Does that make sense? We're trying to build an intuition. We're trying to build an intuition about how things work. So now we need to get into the idea of what's going on here. We want this to go down to 0. We're using these numbers to look for patterns. Our thinking is still, I want this I'm aiming for h equals 0, but then if we do the slope here, we get 0 over 0, which is indeterminate. That's not helpful. In this case, those of you with your secret derivative knowledge, in this case, 0 divided by 0 is 1/4. Don't say it that way when you're Calc 1 students. Later on, when you're math majors and everybody in the room is like, oh, been through calculus, you could say shit like, oh, in this case, 0 divided by 0 is 1/4. And I'd be like, oh, yeah. But if you do it now, your professors be like, oh, no, you don't get to do that yet. You don't get to say shit like 1 divided by 0 is equal to infinity. No, that's off limits to you. It's like when you were 12, you knew what the word fuck was, but you didn't get to use it around the adults because some of the adults would get their knickers in a twist. You know what I mean? But you knew the word. And then eventually you try to figure out which adults you could use it in front of. I remember the first time my goddaughter, she was 12, used the word shit in front of me and her godfather. I remember we were driving somewhere, and I can't remember the context, but I remember her sitting in the back seat trying it out. So I go, can I swear in front of my dad and my godfather? Let me try it out. And it said something like, oh, shit. And we both looked at each other and like, oh, acceptable. We didn't say anything, but she knew it was acceptable because we didn't say anything. And then we're like, oh, don't say that around your mother. And she's like, oh, I'm not an idiot, Dad. You don't get to say 0 over 0 is 1/4 in this case, but it's gonna. So we can't actually plug in 0. So we have to look at what happens as we're headed towards 0. We can't actually plug in 0. Because we need 2 points. H equals 0 means we got 1 point. We need 2 points for this slope business. But we can look at smaller and smaller values of h and see what's happening. We're looking at what's happening as h approaches 0. So we want to say that 0/0 is a quarter in this case, but we can't because that's not technically correct. So we're saying that the slope is approaching 1/4 as the points approach each other. That's so we can be technically correct. And as you all know, technically correct is the best in math class. How's everybody okay? This is the calculus thinking. What's happening as one point gets closer to the other? In other words, what we want is what we call a limit. What is the limit as h approaches 0 of the slope? H can't be 0, but what's happening as h approaches 0? We are calculating a limit. The slope of the tangent line is the limit. LIM is our abbreviation for limits. And then we describe what's happening in this limit. We're saying the limit as h approaches 0. So underneath limit, we write h approaches 0 of the expression. How close is close enough? Until we're sure, or until we're sure enough. Well, the calculator just became sure. We just got within the error bounds of the calculator. Calculator, I see where this is headed. Any questions? How's everybody okay? Everybody looks so sad. Y'all look like this. I do want to talk a little bit about finding the equation of the line, because at this point, I can write the equation of the line through that point 4,2. We can write down we have the slope, we have a point, we have enough for the equation of a line. So I want to do a quick side trip into the equation of a line. I do want to talk a little bit about the equation of a line and how it is structured. The most common one that we have, the most common equation of a line is that we think of y equals mx plus b, right? If I just wrote the words equation of a line and then said y equals, some of you would think immediately, we're trained not to like speak because we get in trouble for talking in class, right? Like in high school. So we beat that out of you, maybe not literally, but psychologically. Which is, by the way, a terrible way to write the equation of a line. Mx plus b. This is how things are changing. Mx plus b. This is where it starts. Tell me where things start, and then tell me how things are changing. We should learn y equals b plus mx. Then all the pedantic ones are like, it's addition is commutative, Leach, so I don't see we need to make a distinction between the two. And I'm like, oh yeah, we think about addition and the fact that it's commutative. That's why we get to call it addition. But not everybody thinks about addition as being commutative. And all the mathematicians are, but it is. You mean our students aren't automatically thinking, oh, you're calling it addition, but they're not thinking of commutativity. No. That you know that, right? You all knew this. 2 plus 3 is the same as 3 plus 2. Addition does not care what order shows up in. But you don't think of addition being commutative. You know what I mean? Mathematicians are out of touch. That's the point I'm making. So we have our normal equation of a line, the one that we all like, mx plus b, which is kind of trash. Or start here and do this a bunch of times. That's why I like b plus mx. Start at b. Y starts at b when x is 0, and we add m a bunch of times. It literally tells you how the function works. But that's beside the point. I didn't bring my soapbox today. I need to shut up. This is called the slope-intercept equation, or slope-intercept form. Because we have a slope of m, and we know the y-intercept is 0b. This is fine for just describing generic functions if we care what's going on when x is equal to 0. We don't always care what's going on with x equals 0, like the example that we had on the previous page. We care what's going on near the point where x is 4. I care about what's going on when x is 4. I don't care what's going on when x is 0. So we use a different form. We can use a different form of a line. That way we can write down the equation of a line and not do any calculations. Anytime you can avoid calculations, avoid the calculations. Anytime you know how to skip a step in a math problem, you should skip that step in a math problem. That was the point of the math class. The point of the math class is to not write all your steps. The point of the math class is to get to the point where you don't have to write all your steps. That's the point. You know what I mean? It's like we're deliberately slowing you down. Ridiculous. So here's the other function version where y is a function of x to write the equation of a line. This is point slope form because the information it contains is a point and a slope. We're very clever coming up with the names here in math class. So this is the point. So the point slope form is y equals y naught plus m times x minus x naught. If we just choose x naught to be 0, then y naught will be the y-intercept, and we call that b. So this one is just a more general form of the other one. If x naught is equal to 0, then that term becomes mx, m times 0, no change, just b. So in the example we have previously, if we have a point 4, 2, and slope of 1/4. Instead of doing any calculations, I'll just say y is 2 when x is 4. Y starts off at 2. And we add 1/4 whenever x increases by 1. Now we can simplify this and write the slope-intercept form, but we don't need to. And anytime you start multiplying some numbers and writing down new numbers, you take a chance that you've just messed something up. So if this will suffice, then let it suffice. Write everything you need, write only what you need. If we're going to write this in single line syntax, so like you're typing, I just give you a little box to type your answer and you only get a single line. You can't do superscripts or subscripts or make fractions or anything like that. If we're typing this in single line syntax, that fraction will need parentheses. So you'll want to write y equals 2 plus 1/4 x minus 4. So in single line syntax, this would be the easiest translation. Just put the fraction factor into parentheses. That would be the easiest conversion. So if, like during a test, you need to text your friends the answer since you can't do subscripts and superscripts and fractions on your phone. I'm just kidding. That would be ridiculous. I mean, you have a camera on your phone. Take a picture of your work and mail it to them that way, or text it to them that way. Can't believe it. I have to teach some students how they're supposed to teach. Good question. How's everybody okay? Okay. So the last thing I want to think about is the way we think about linear functions. Mostly because we have other kinds of functions that we need to deal with. Our favorite are going to be linear functions. The reason our favorites are linear functions is that's our default mode of thinking. Our default mode of thinking is to just draw lines between things. Our default thinking is to just think linearly. If you think about splitting the difference, that's making a linear function. We're negotiating. I say 5,000, you say 3,000. We agree to split the difference and land at 4,000. Split the difference. That's thinking linearly. You're just drawing a line from 5,000 down to 3,000 and going halfway on that line, it'll be at 4,000. That's why if I have the higher value, I want to make a different function. So I don't want to split the difference linearly. I want to split the difference, say, with like a square root. Bends the graph concave down. Here's how we want to think about the reason I like to write b plus mx, because this says, it says y is equal to b. Let's just look at how it starts. Y is equal to b. If there's no changes, just stop there. Y is equal to b, like the equation in the line we had before in the second problem. Y is equal to 4. Done. Y have the starting point at the end of your sentence. So it says y is b when x equals 0. So we think y starts at b. Then the next thing in the sentence is plus m. Then add m. And we do that a bunch of times. And the x is standing for a bunch of times. So that's why I like writing it this way. Also, when we go to write exponential functions, the only difference is instead of saying add m, we're going to say multiply by m. But it's still going to be a bunch of times. We'll talk more about exponential functions later on. If you have a point that's not the y-intercept, just use point slope form. I've mandated that you use point slope form because I don't know, it's just American authoritarianism. Do it my way. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.